Welcome to today's topic, finite element method for the eddy current problem. So there are a few methods, formulations for the eddy current problem. You can find them in the reference given here by Oscar Pirot. We will focus on the very common magnetic vector potential formulation, also called A or A star formulation for an ungouged formulation, where the magnetic flux density is defined as the curl of the magnetic vector potential A. We also look at the eddy current problem in the A formulation. So we consider domains with generally varying magnetic permeability and varying electrical conductivity. In some domain parts, the conductivity could be zero. And for the sake of simplicity, we assume all these parameters to be constant in the specific subregions. So then we have the strong form of our PDE with introducing the magnetic vector potential A. And this is what we need to solve. We've also seen last time that we need to satisfy some physically motivated boundary conditions, being the normal magnetic flux density jump over an interface must be zero, and the normal eddy current density jump also must be zero. So the current is continuous over an interface, or the normal direction of the current is continuous. And the tangential magnetic field intensity must be zero. The tangential magnetic field intensity is given by the HXN expression, and this is only zero if there are no surface currents, which is the usual case, let's say. As a first step, we'll be splitting the vector potential into its normal component with respect to a normal vector given, for example, at an interface. So we split it up in normal and tangential component. The normal component is defined with the help of the normal vector, and the tangential component is simply the complete A vector minus the normal component. That can also be written as NXA_XN. And if we do this, we see that the normal component of the curl of any field A is uniquely defined by the tangential component of the field only. And you see this when you do the math. You compute the normal component by the help of the inner product with the normal vector that gives you the normal component. You split the A into A normal and A parallel. And what you then see is that the curl of A normal in the normal vector is always zero. This is the definition of the curl. It has to be orthogonal to the original component. So if you take the curl of the normal component, it's orthogonal to the normal component, so the inner product must be zero. Okay. When we now look at the tangential component of the vector potential, we can look at the normal continuity of the flux density. So we actually want to compute this physically required transition condition. Here we can then see that we only need the parallel components for this. So only if the parallel components match, we have zero parallel components of the magnetic vector potential match, we have zero jump in the normal flux density. In fact, you can do this equivalently when looking at the flux through a surface perpendicular to an interface. That also needs to be zero if you make this interface small, and this flux can actually be computed. it's related to the surface, to the line integral over the boundary of this surface, and this line integral is given by the two lines that not tend to zero when you make this interface infinitely thin, and these lines are given by the tangential components of A. So to sum up, the tangential component of the magnetic vector potential must be continuous in order to satisfy the physically required bound interface condition on the normal component of the magnetic flux density. Let's look at the next physically required interface condition, and this is the normal continuity of the current density. Current density is given by the time derivative of the magnetic vector potential multiplied by the conductivity. And if we insert this here and we introduce the jump, we see, okay, this expression gamma 1 times A1 normal minus gamma 2 A2 normal, this is only zero if we have a certain relationship between the A1 normal and the A2 normal. This relationship depends on the electric conductivities. So we can only make this zero if the A1 normal and A2 normal are in generally different, so they are not continuous. So the normal component of the magnetic vector potential must be discontinuous at interfaces with changing electrical conductivity. We can look at the third magnetic or physical condition we need to satisfy, which is the tangential continuity of the magnetic field strength for the interfaces without surface currents, just for the sake of simplicity, and this we will introduce here again with the expression AHXN. And for H, we now insert the B field, and for the B field, we insert the curl of A. So this needs to be zero. And now let's again write out the jump term and split the A into its normal and its tangential component. So this is just the split inserted here. And now we can, for a test, just assume what would happen if we have the tangential continuity of the magnetic vector potential. Then we can collect the A1 and A2 parallel terms together. We have the difference in the permeability in front, and we have also already seen that we need normal continuity of the vector potential. So we can also collect those together. So we can collect the A normals together, and this expression should be zero. And we can think, yeah, when could it be zero? This can either happen if we have no permeability jump, so V1 is equal V2, then this gets zero. But this is not the general case. The only other option is that the magnetic vector potential is zero everywhere, but this is also not the solution we want to. So our original assumption requiring tangential continuity of the vector potential will violate the physically continuity condition on the tangential component of the H field. So to conclude this, the normal component of the magnetic vector potential must be discontinuous at the interfaces with changing magnetic permeability. So this has a few consequences for the finite element ansatz functions. In the general case, we need the tangential component of the magnetic vector potential to be continuous. and the normal component of the magnetic vector potential has to be able to jump. And this is not satisfied by standard nodal finite elements, because those, of course, would enforce the continuity of both normal and tangential components. So nodal elements will only be valid in a 2D setting. Here, the vector potential that we consider is actually only the third component, so the tangential component pointing out of the computational plane, or if we don't have any jumps in magnetic permeability or electric conductivity. But this also is not the general case. So in general, nodal elements are invalid in a 3D setting. We now want to derive the weak form for the eddy current problem. We do this in the usual manner. We take the strong form, multiply by a test function A prime, and integrate over the domain. Then we can use the vector identity for the divergence of the curl of two fields. And we can insert this to rewrite the second term. And when we have done this, we again see a divergence term appearing. And on this divergence term, we can, of course, use the Gauss integral theorem to rewrite the divergence in terms of the boundary flux. And here we can introduce nxh to be the surface current. So this is a known quantity. If we have if we know the surface current density, this gets an inhomogeneous Neumann type condition. And if it's zero, it gets the natural Neumann type condition. So here we have the final weak form, where we have some mass time form with the first time derivative of the A field. We have the curl operator, so stiffness type form. And we have right-hand sides that can consist of prescribed impressed current densities we know somewhere in the domain, and some boundary surface current terms. So we've seen nodal elements are not suitable for the curl problem. What is suitable are so-called Nedelec or edge finite elements, and they have edge-type ansatz functions. So we build up the A field as usual as a combination of space-dependent ansatz functions. They are vector valued, so boldface EK. And for each edge K, we have one ansatz function that we multiply with one coefficient AK. And these unknown time-dependent coefficients associate each edge with the corresponding integral of the vector potential along the edge. In fact, in practice for engineering applications, the meaning of this coefficient does not matter so much. We are primarily interested in the curl of A as the magnetic flux density. So now the question is, how do we define these vector valued ansatz functions? And it turns out that you can compute them from the standard Lagrange type ansatz functions for nodal finite elements. So you can use the gradient of edge J and multiply it with the ansatz function for edge for node I minus the ansatz function for node J times the gradient for the ansatz function for node I. And this is the edge going from I to J. Okay, there are several variations of Nedelec elements. They can be formulated for various orders. There are different kinds of elements with the first kind having only edge degrees of freedom for order 1, and the second kind, for example, with 2 edge degrees for order 1. And typically higher order Nedelec elements will also contain phase or volume degrees of freedom. They are also often called H-curl or Whitney elements, or simply edge elements. You can find a lot of details regarding especially higher order finite elements for the eddy current problem in the PhD thesis of Sabine Zagelmeier. And if you're interested in visualization of the ansatz functions, there's a web page for it. If you now do integrate the weak form and compute the resulting matrix system, you see that we have again a mass type system paired with the first time derivative of the unknown vector and the stiffness type system on the right hand side. So we have a first order ODE system for the eddy current problem that can be solved with the standard time integration problems. So again, the mass matrix has mass type ansatz functions without any derivatives, and the stiffness matrix has differential operators involving spatial derivatives being the curl operators. So let's look like how these operators look like. In fact, we've seen the definition of the ansatz functions already that already take gradients of the Lagrange type ansatz functions and the curl operator that is the curl of this ansatz function. So this example shows you how to compute the curl operator. Now let's move on to boundary conditions for the eddy current problem. In fact, the natural boundary condition for the weak form is 0 surface current density, so Hxn is 0, and that forces the magnetic field to impinge the boundary in normal direction. On the other hand, an homogeneous Dirichlet condition, so eliminating the edge degrees of freedom, will lead to normal flux density of 0, so the magnetic field lines will be parallel to the boundary. In general, the magnetic fields should decay away from the excitation. So if you have a coil somewhere in the domain, the magnetic field will decay away from this coil with the rate of 1 over r to the power of 3 in 3D. So whenever you truncate your computational domain, you will make some mistake. So the boundaries should be sufficiently far away. Of course, it's the question, what does sufficiently far away means? The choice between the natural and the homogeneous Dirichlet conditions does not matter in this case. If the boundary is far away, the direction of the field will not be will not matter. It should be 0 anyway. The homogeneous Dirichlet condition is maybe a little bit preferred because first it eliminates degrees of freedom. You have to solve for less degrees of freedom, and it forces the field lines. It forces closed field lines within the domain, which might be beneficial. Also, remember that in magnetics there are 2 different symmetry planes. First, we want to we can have fields parallel to the boundary and fields normal to the boundary. So let's look at the example of the flux parallel condition. Here we have the magnetic flux density B that should be parallel to the boundary. So the inner product with the normal vector must be 0. In this case, we have the condition that it is parallel. And to enforce this condition, the normal component BZ, of course, needs to be 0. The question is, what does this mean when we have the B field defined as the curl of the vector potential? So the vector potential now has also 3 degrees of 3 components, AX, AY, AZ. If we build the curl of this and we want to have BZ0, we see that this is only satisfied if the AY and AX component are both 0, and these are actually the tangential A components of the vector potential. So for vanishing tangential components, the flux will be parallel to the interface because the normal component of the flux density BZ needs to be 0 in this case. Here is an example of magnetic boundary conditions or magnetic problem. We have this green conductor carrying some current through the domain. We have an iron core that, of course, will concentrate the field a little bit. But for the top and bottom phase, we want to require a tangential field lines for these 2 symmetry planes, the XZ and the YZ planes. We will have the natural boundary condition, so we don't need to do anything in order for the flux to be orthogonal to the interface. So this, of course, happens if the parallel component of B is 0. And for the outer boundary, again, we take the homogeneous Dirichlet condition on the edge degrees of freedom, making the flux parallel to the boundary. For a 2D case, we already mentioned that this is a case where we only consider field lines within a 2-dimensional plane. So in our case, by convention, the XY plane and the magnetic vector potential then only has a Z component, which is perpendicular to the plane. So we only have the Z component, and that enforces our field as the curl of this magnetic vector potential vector having only X and Y component. So it stays in the considered plane. It's similar to the axis. This is similar to the axisymmetric case. The only main difference is that the meanings change and that the curl operator gets a little bit of a different form. So again, we only work on the radial component of in fact, on the circumferential component of the magnetic vector potential. And instead of a 2D simulation, you can also use 3D edge elements. Use a wedge that is a small angle cutout with 1 layer of 3D elements. And for the front and the back faces of this wedge, you remove all edge degrees of freedom. So what remains are only the circumferential edge degrees of freedom, which then corresponds to the degrees of freedom in a true 2D setting. So now we have boundary conditions. Of course, we also need excitation conditions. And in general, this can be done in several ways for the eddy current problem. The most important is perhaps a standard stranded coil, where we know the impressed current density in some region omega I. And due to this, eddy currents will be introduced somewhere else in the domain, but not in the impressed current region, where we have to set a 0 conductivity. Otherwise, we would introduce unphysical eddy currents there. Other forcing options are, of course, the surface current on the boundary of the domain, or permanent magnets where we have the curl of the magnetization prescribed in some known region. In fact, surface currents and magnetizations can also always be seen in an equivalent way. And the last but very important excitation condition is so-called electric ports, where we have some massive inductors that will introduce, that will carry eddy currents also, so conductive regions that have some boundaries with the edge of the domain where we want to prescribe some given current or voltage between these ports. Okay, so let's look at these electric ports a bit more in detail. So we consider some conductive region, omega C, that has boundaries with the domain boundary. So this gamma plus and gamma minus, and those will be our electrical ports. And assume we want to prescribe a voltage difference at these ports. What we then typically want is either this voltage difference or some normal current density or total current density that goes through this inductor. But this inductor will, of course, also allow the development of eddy currents in it. And now it can be shown that we don't need to do a full AV formulation where we also have voltage degrees of freedom for every point in the conductive regions, but that this can be solved in, they can be computed separately. So there's a mathematical proof on this by Hiptmeyer and Sterz. You can look it up if you're interested. A bit of a summary of this modified A formulation is given in the PhD thesis of Klaus Roppert, and there are extensive works of Patrick Dulard on this type of formulations if you're interested in detail. In the following, I will just introduce how this formulation looks then in the end. So let's look at the global voltage excitation first. Here we apply excitation voltage between those two ports, and the resulting current density is then on the right-hand side. And what we need to do for this current density is we have to pre-compute a unit source electric potential V0, and this can be computed by a current conduction problem on these conductive regions with zero boundary condition at one port and one, so unit voltage boundary condition on the other port. So that gives you the V0, you can pre-compute it, and then you feed it into your weak form equation 81 that actually then looks equivalent to an impressed current formulation. The only difference is that you don't prescribe directly the impressed current, but it is computed as U0 times gamma times the gradient of V0. An important note for this formulation, the appropriate boundary conditions on the ports is the flux parallel condition that actually forces the resulting currents and eddy currents to be perpendicular to the boundary. And now let's look at the global current excitation. If we prescribe the total current through the port, the necessary voltage is unknown. So this term will come from the right side of the equation to the left side, so unknown scalar U. And we need an additional equation to actually determine this unknown voltage. And this additional equation is the current conservation, so the divergence of the eddy current, gamma times E, needs to be 0 in the conductive region. And then we can insert here the definition of the E field for this formulation. That's the time derivative of the vector potential plus the voltage. And this gives us equation 38, which is a scalar equation. The I on the right-hand side actually comes from the handling of the boundary terms. So the current density integrated over the boundary, of course, is the total current on the right-hand side. So this gives us a second equation together with equation 81. And you see, when you look at the equations in detail, this is actually an unsymmetric system which can be symmetrized by introducing the unknown defined as the time integral of the voltage. So you can do this. This is a choice of unknown. And if you introduce this change of variables, you obtain a system of equations in the weak form that is actually symmetric, because those two coupling terms, the terms with the vector potential and the gradient of V0, these are then symmetric in equation 48 and 40, 84 and 85. Finally, a bit of notes on the time discretization. So we've seen the semi-discrete Galerkin system is of first order. So we can introduce a time stepping scheme. We subdivide our time interval into, for the sake of simplicity, equal intervals with some constant time step, delta t. We choose a forward time difference scheme for the derivative. And then we can decide at which point we want to evaluate the elliptic part and the right-hand side. And this decision is formulated by the weighting parameter gamma p. And based on this parameter p, we can either get a fully explicit or fully implicit time stepping scheme, as you can see here. Yeah, so there's some specific choices for gamma p. So 0 would be forward differences, so forward explicit forward Euler, which is in generally not stable, or at least not unconditionally stable, which is what we want. 0.5 will give us a Crank-Nicolson scheme, also called the trapezoidal rule. And 1 will give us a standard backward Euler scheme. In general, one should use implicit schemes, and the Crank-Nicolson will be of second order, so perhaps preferable. As a rule of thumb, one should have about 20 time steps per smallest excitation period. What you can also always do is factorize the effective system matrix for linear problems, prefactorize it, so the time integration will be fairly fast. For eddy current problems, there are a few post-processing results of interest. Of course, the edge values for the magnetic vector potential are hard to visualize because they're defined on the edges. You could evaluate A based on the ansatz functions in the centroid of each element, but the actually interesting part is the magnetic flux density to the physical field defined as the curl of A. You have the electric field in case you have some electric ports. You have the additional U times gradient V0. You have the eddy current density that comes from the electric field multiplied by the conductivity. And you have integrated results like total currents, which are current densities integrated over a boundary gamma, for example. In openCFS, we have several magnetic formulations implemented. One is the nodal elements, so the magnetic PDE, which is useful for 2D and axisymmetric cases, and the edge elements, so the PDE then is called mag edge for 3D cases, and some additional formulations are available in openCFS, for example, the AV formulation. You can use this formulation tag on the magnetic edge PDE tag to activate those, where you can prescribe voltage boundary conditions at electric ports, or the more efficient version, this modified AV formulation, where you don't have to solve for any voltage degrees of freedom, as was explained beforehand. So this is then called in openCFS spatial AV formulations. Again, details are available in Klaus Robert's PhD thesis. Now, a few words to modeling of eddy current problems. So typically, you should start from magnetostatics and check the field results to determine if your boundary conditions are as expected. Then you switch to an dynamic or frequency domain eddy current problem. It's always good to visualize the H and B fields as vector fields, for example, using flux tubes in ParaView, for example. An important point is, of course, you need to resolve the skin depth in eddy current regions with approximately 10 elements within the skin depth. You can use appropriate grading to resolve the boundary layers that will help you there, not using excessively many elements. You can use P refinements of elements of higher order to get better convergence measures or convergence rates. What you should also avoid in eddy current regions is tetrahedral elements, because they have bad convergence properties, much worse than hexahedra in this case. Stranded coils, so prescribed impressed current densities need to be modeled with zero electrical conductivity, so there are no eddy currents created. And if you, for example, have the flux not impinged into a conductive part, check if you have resolved the skin depth sufficiently, or if your conductivity values are reasonable. Here are some questions on learning reinforcements that you can look at. And finally, here are the references I cited in the talk. Thank you.